Good morning, everyone. So let's begin with today's session, and we are going to continue with the topic of self-induction. And we just go through what we had done yesterday, kind of brief summary of what is self-induction mean and what is the sequence. So if, that's how I think you can summarize. So if there's a coil, if a current I flows into a coil, what is the effect of current in the coil? So we can see in the logical sequence how things happen, how one things lead to other. What would current lead to? Whenever there's a current in the coil, it creates a magnetic field. So there's a coil creates a current. If there's a current flowing, it creates a magnetic field. And if there's a magnetic field, there's a flux through the area enclosed by the coil. Okay, so to calculate flux, so whatever shape the coil is, if you have to calculate flux, I need to the value of field at all points in the area occupied by the coil. Sometimes it is easy, sometimes it is difficult to calculate. But what we know is current leads to the magnetic field, and magnetic field leads to flux. And since the current is directly, magnetic field is proportional to current, and flux also is proportional to current, which basically means if in a coil, if I double the current, what will happen? Flux through the area bound by the coil also will double. And that's how we write. So flux is proportional to current. And any two quantities are proportional, we can have a constant of proportion. So self-induction is essentially based on expressing flux in one more form. So far we used to write flux is equal to what? B dot dA and summation of that. We can also write as Li. Li is a term called coefficient of self-induction or self-inductance. So rather than writing phi, so once we know for a given shape, what will happen this L term, what will L depend on? For as long as shape of the coil does not change, L will remain constant. If we de-shape, if we change the dimensions of the coil, L will change. So until the dimension of coil is changed, L will remain constant. For a given coil, L is a constant. How do we use it next? So when the current in the coil changes, B changes, flux changes. I can directly look at this equation also. Whenever the current changes, the flux will change. And whenever flux changes, it leads to induced EMF. So first thing we understand in case of self-induction, we express phi in terms of phi is flux through a coil is equal to Li. I is the current in the same coil, and this term L is constant of proportion. This depends on the geometry of the coil. So EMF, every time when we calculate EMF, so far until the topic of self-induction, we used to write EMF and we're just writing magnitude, direction using Lenz's law. EMF is equal to d phi by dt. Since I have one more way to write flux, I can write in place of phi Li. So L is a constant. As long as it is not being deformed, it becomes L di by dt. And how do we find direction? Based on Lenz's law. If current is tending to increase, it will oppose the increase. So when the current is increasing, this EMF acts opposite to direction of current. When current is decreasing, it acts in the direction of current. And based on this equation, for a LR circuit has battery, inductor, and resistance. That's what we call as LR circuit. We write Kirchhoff equation, and Kirchhoff equation, if we integrate and rearrange the term, this equation we get very similar to RC circuit. And this equation gives you value of current at any instance of time. So if we connect a battery to LR circuit, and at time t is equal to 0, we close the switch. See, current does not rise to the full value immediately. Current rises gradually, and this is something the shape of the curve also will plot. I think some of you recall, and we should understand this shape. So if you look at the current here, the current gradually will rise something like this. And this shape we are familiar with. This shape we have seen in case of how the charging of a capacitor takes place in case of RC circuit. Here, this curve is called charging of an inductor. The inductor, gradually the current increases until it reaches a maximum value. We can call this current I naught, and I naught from here very easily we can calculate when t tends to infinity. I naught is E by R, which is same value of current as an inductor is not present. So at a steady state, inductor offers zero resistance. So this is LR circuit, and we are familiar with some of the terms. This term equation is very similar to this equation we have seen before. Tau is called time constant. Earlier seen it was RC, now it is L by R. This is what we need to remember. Time constant is L by R. And this equation, this is easy to remember. What is I naught? I naught is E by R. EMF in the circuit divided by the total resistance. And what happens when we connect a number, if we have a combination of inductor? So if two inductors are connected in parallel or series, is very similar to resistance. When it is connected in series, summation. And when it is connected in parallel, 1 by equivalent inductor will be summation of 1 by L. Okay, so this is the, in terms of theory, those are the points what you need to know. Let's look at some simple applications of the same. And what we have done, most of it are direct application of basic formula. Let's look at one of this question. Let's look at a couple of few of them. So what is the length of the wire required to manufacture a solenoid of length L so that it has a self-induction of L? If cross-section area is negligible, so how is the solenoid? See, rather than saying it's a long solenoid, we can also say the radius is small. Both mean the same thing. When you say long solenoid, it means the length is much less than the radius. Or same thing can be said in cross-section area is negligible. It is one thing is stated in 3 different forms. So it is something like this. You understand, I hope, what is solenoid. It will be something like a long pencil kind of thing. You wind wire on this and you get a solenoid. So what is the length of the wire required to manufacture a solenoid? So this is pretty simple question. It is based on 2 simple equations. What is the length of the coil? If I use normal variables we use for solenoid, length of the coil will be how much? How do we find the length of the coil be equal to? Length of the coil will be length of the coil in 1 turn multiplied by number of turns. So 1 turn will equal perimeter into number of turns. And if I take the radius of solenoid as a small a here, so perimeter will become equal to 2 pi a. And number of turns, how do you write number of turns? We use term N to indicate number of turns per unit length. Here length of the solenoid is given, so number of turns will become equal to N into L. So this is length of the coil, that's what we need to find. But here the length of the coil required is mentioned in terms of L. So to find an expression in terms of L, I need to write an expression for this L also. What is value of self-inductance in case of a solenoid? It is equal to mu naught into N square times volume. So this also can be written as mu naught. Volume can be written as what? The area of cross section, pi a square into L. Okay. So when we look at this, which term is missing here in this case? This is what length. Length here, which term is missing? A term is not there. So all we need to do, we need to eliminate which 2 terms, N and A. So we substitute value of NA from this equation into this equation, we get our required answer. So this is something part of assignment, all of you can easily solve. So these are nothing but manipulation of formula. It doesn't give any great new insight. Another similar question is like this. So inductance of solenoid of length L, whose windings are made of material of density D is given, resistivity rho is given, and winding has a resistance of R. So this question also, in my opinion, this has practically no new, it has no physics insight, but this question is then material, so you need to solve it, and it's a simple question. Not little tedious. So many variables involved. So let's see what are the things which it involves. I'm just giving a hint. All of you need to solve. Pretty simple one only. Again, let's assume the radius of solenoid is A, and there's wire also. You understand there are 2 different radius of solenoid and radius of the wire. Why what we use in winding? Why this radius is required? Because the density and mass is also given. There's a term mass also. So we assume the radius of solenoid to be A, radius of wire to be R. What are the terms which are relevant here? We need to find the value of inductance. So let's write what is inductance is equal to. Inductance is mu naught into N square V. So I could have written number of turns equal to total number of turns divided by L. So it's simple. I've just substituted these values. This value of L. But here the answer is not in these terms. There are some other terms also. So we need to look at what other terms are relevant here. Other terms is mass is also given here, and resistance is given. So what I need to do, again, I need to substitute some values, eliminate some of the values here. Let's write what is the resistance equal to. Resistance equal to rho into length of the wire divided by cross-section area of the wire, not the cross-section area of the solenoid. Cross-section of the wire. And what is the length of the wire? We have seen earlier also is length of the wire in 1 loop multiplied by number of loops. That's R value. And what will the mass be equal to? Mass will be equal to density into volume into length into cross section area. So these two terms we have. So when we look at this from here, we need to substitute something in terms of R, and we need to make suitable substitution and get an L value depending on what is needed here. And this is not a complex question. It simply requires mathematical manipulation. This is also part of assignment today. All of it we can easily solve. No, I don't think any physics concept is involved in this. Now coming back to question of time constant, we have dealt with time constant in case of RC circuit. Here also we'll go through some questions on time constant. What is the time constant in case of, again, just to quickly recap, time constant in case of RC circuit, in case of RC circuit, time constant itself is equal to RC. But in case of LR circuit, time constant is equal to L by R. Okay, so what is given here? This also is a fairly simple question. When a pure resistance of R ohm is connected in series, this is so whenever we add a resistance in series, R will increase, time constant will decrease. That's what it said. Time constant is found to decrease to tau 2. They have used a word called internal resistance of inductor. Let's understand a little bit what this term internal resistance of inductor means. See, typically if we have a LR circuit, how we draw an LR circuit, this is typically how we draw an LR circuit. There's a battery, and then we show something like this, which is indications, this sign what we use for inductor, and then we use a resistor here. Okay, but does it mean this inductor and resistor are necessarily two different current elements? Actually not. See, this inductor, one way of thinking of inductor is a solenoid. It has a winding. So does it have significant length? Yes, this winding coil has significant length. So will it have resistance? Of course, any inductor will have resistance. Though resistance is part of the inductor, for simplicity, we show it separately. So in addition to inductor, there could be separate resistance also, but any inductor will have resistance. I hope this point is clear. Inductor is nothing but a conducting coil. And if there's a conducting coil, has to have some finite value of resistance. And that's called internal resistance of an inductor. There may be additional resistances also. Okay, so internal resistance of the inductor. So this question, otherwise solution is very simple. Only thing what we need to understand, all inductors have resistance as well. They always coexist. It is impossible to have inductor with zero resistance unless it is a superconductor. We can say the resistance may be very small, but it is always a finite value. Though the circuit diagrams show two of them separately, it doesn't mean they are two separate entities. Their behavior is separate. So in terms of understanding their behavior, conceptually we draw as two different elements, but they coexist as well. So now this question is fairly simple. What is the initial time constant of inductor? Tau 1 was equal to L by R naught. Let's assume R naught is the internal resistance. If we add one more resistance here, this was R naught here. We have added one more resistance R here. In that case, what will be tau 2 be equal to? In case since it is added in series, it will become R naught plus R. R is the external resistance. That's what is given here. What we need to find? We need to find the value of R naught, which is fairly simple. Very easily we can find. Important point was only to understand what does internal resistance of an inductor mean. So far, anybody has any query? This is so far we are just going through the basic formula application. So nothing much here. Now let's come to this question. Ratio of time constant in charging and discharging. So we'll understand a little bit of charging and discharging. But I can also draw the similar circuit in a slightly different form. You see, let's try and understand what that form means. One way, in this case, this is another one. Let me draw another one, something like this. So this is something like this. There's a switch here. There's a two-way switch here, and this resistance is 2R, and this is how it is connected. Okay, and let's say this is R, and this is 2R, and this is an inductor. And if you recall, we might have seen something similar in case of RC circuit. Let's call this point as A, B, and C. Let's see first what is connected. What does charging mean? What has to be arrangement of two-way switch for charging? What is, let's please understand what does charging of inductor mean. Charging of inductor basically making current flow in the inductor is called charging. Similarly, making a current flow in inductor is called charging. What is charging of a capacitor mean? Giving charge to a capacitor. So there what we do, as we keep increasing Q, we say the capacitor is getting charged. And similar way, what we'll call as inductor as, can you similar way, can somebody give me a statement? So what I said, in what is charging of a capacitor mean? As long as we keep increasing charge on a capacitor, we say capacitor is charging. What is capacitor discharging mean? When the charge on the capacitor starts decreasing, we call it discharging. Can someone say similar way, what is the charging of inductor mean? As long as the current keeps increasing, inductor is getting charged. And what happens when the current starts decreasing? Inductor is getting discharged. Okay, that's the understanding of charging and discharging. So there, every term in case of capacitor is in terms of charge. Here it is in terms of I, current. And that's why we recall the formula also. How do we write charging formula for a capacitor? We write capacitor Q is equal to Q naught 1 minus e raised to power minus t by tau. This is charging. And similar way, how the charging for an inductor is written, I is equal to I naught final current, which is equal to V by R 1 minus e raised to power minus t by tau. And what is the discharging formula in case of a capacitor? Discharging means charge starts decreasing. And in that case, this was equal to Q as a function of time will be equal to Q naught e raised to power minus t by tau. What does Q naught indicate here? What does Q naught indicate here? Tejas, can you tell me what is the Q naught in case of discharging of a capacitor?
Yes, sir. It's the initial charge that the capacitor.
Initial charge. The moment you start discharging, this is the charge just at the instant charge starts decreasing. That's an initial charge. Similar way, this also will be equal to, if I write discharging, it will be I naught e raised to power minus t by tau. When does this happen? That when the charge starts decreasing. Typically, we say when the battery is not there. So let's see in this case also, what is the charging of this circuit mean? So one way, if I have to charge this inductor, when we are charging is, what is the connection I need to make? When B and C are connected. When B and C are connected, what will happen here? This inductor will start charging. And how will the current be if I take this current through the inductor as I here, IL? What will the I as a function of time be? I as a function of time will be equal to I naught e minus e raised to power t by tau. Let me put those values. What will be I naught? In place of I naught, I can substitute B by 2R. And that's the EMF of the loop divided by 2R. That will be the final current which will flow through. This will be the final current which will flow through at when it is fully charged. And tau value, what we substitute in this tau value will be equal to L by R. So it will be L by 2R here. Is this understood? Pranav?
Yes, sir.
Kevin?
Yes, sir.
Okay, so this is something charging in. So Kevin, can you tell me what I need to do for discharging? See, I have given you some statement. Have you understood what is charging mean? Current will increase. Can you keep, and I have written here when B and C are connected, if this is the connection here, which connection we have made for charging. So if I show in color, the red color, this is the two-way switch. When I connect it like this, it will charge. Similar way, Kevin, can you tell me what is the connection between which 2 points I need to make connection for discharging? Discharging means what? What connection need to be made for inductor to discharge? Anish, can you tell me what does discharging mean? How do I need to change the arrangement of the switch for discharge? Anish?
By connecting A to C.
Connecting A to C. So moment I flip the switch from here to here, what will happen? Battery will go out of the circuit and will start discharging. So in that case, what will happen? The current will flow. Where from the current is coming? Actually, the current is coming because of the inductor. And if you recall, in case of discharging of capacitor, capacitors provide energy after the battery is removed from the circuit. So whatever energy it has stored in form of a charge, it charge reduces, means energy in the capacitor reduces. That energy is utilized for flow of current. Something similar happens here also. Even after the battery is removed, we'll find the current will flow. In place of resistance, if we have bulb, we find even if the battery is removed, the battery bulb will glow, though the brightness of bulb will keep going down, indicating that yes, still there's some energy in the circuit. Where from the energy is coming? That energy is coming from energy which was stored in the inductor. We'll come to energy part little later. So what does discharging mean? When I connect C to A. Mode I connect C to A, it will start discharging. If I start discharging, can I write value of how would current vary as a function of time? Jaideep, can you tell me what will the equation of current be now?
Sir, it will
Evidence
be
something here. Okay, so what we need to write this equation. What is the I naught here? What should I write as I naught?
V by 3R.
No, it's a V by 3R.
No, sir, V by 2R.
V by 2R. Are we clear? Because just before it was discharging started. What is I
It will
naught?
be 3R near the time constant.
Yes, very good. So that's what you have to understand. V by 3R, so we have already answered that question. Second question I was going to ask. So I hope this question you understood. What is I naught? I naught indicates what is V by 2R. V by 2R indicates current just at the instant discharging starts. Current at the instance discharging begins. And that's not very surprising. The discharging begins. So I can write. And what will the time constant here? The time constant, we see when the discharging state, what would be the relevant circuit for discharging state? If I had to draw the circuit for discharging state, discharging the circuit will be like this. This will be the part of the circuit. This is the circuit. This is the discharging circuit. And you notice in case of discharging, the resistance becomes equal to 3R. So when I take discharging state, when I write time constant for discharging state, equivalent resistance will not be 2R, it will be equal to 1 minus e raised to power minus t by tau. But tau value will be equal to L by R effective. What is the equivalent resistance in the discharging? L by 3R. This is in this case. This was simpler to understand. Now coming to this case. In this case here, when we talk about charging here, charging capacitor, see, if I write this current at an instance time t, this is, let's say this is I2, this is I1, and this is charging state. Of course, this will be I1 plus I2. Which current is actually charging here? I1 plus I2, I1 or I2? Which current is flowing through? Actually, I'm concerned what is the current flowing in the inductor. That's the charging time. So what would I1 say in this case? Will the current in I1 be affected by presence of R or not? Will the charging of inductor be affected by presence of this resistance or not? Bhagishri?
No, sir.
Huh? So I write, how do I write? See, if the resistance R was not there, how would I have written I value? I would have written I is equal to I naught 1 minus e raised to power minus t by 2. Then I have to find only two values. I have to find I naught. So this I am writing for what? I am writing for inductor here, I1. So what will the final, if the R was not there, what would have been value of I naught here, Bhagishri?
I1 plus I2, sir.
No, in terms of voltage and 2, what will be the I naught indicates current after a long time flowing through inductor. So if this R was not there, I am taking the case when R is not connected.
V by 2R.
V by 2R, when R is not connected. I am trying to understand what will happen, what is the effect of R. To understand the effect of R, first I am seeing if R was not there, then what happens, and then let me see if R is connected, what happens. If R is not connected, and it's pretty simple. It will be equal to V by 2R. And when I write e raised to power minus t by tau, the value of tau also is simple. Tau also will equal to L by 2R. Now, just think of if R is connected. Will this equation change if R is connected?
No, sir.
How many? Why not? Tell me why.
Sir, initially after the switch is closed, I think the resistance of L will be 0.
Now, you see, that is one way. Think of it. But see, if I write, see, suppose I, how this equation was derived here. So again, we can go to very basic also. Sometimes a little bit of doubt. Let's think from very basic. How do you arrive at this equation? By writing a Kirchhoff loop rule for this particular loop. So if I write Kirchhoff loop rule, now there's I1 and I2, both are there. This is I1 and this I2. So how would I write Kirchhoff loop rule? So if I had written Kirchhoff rule, I would written V equal to I1 into 2R plus I1 into, sorry, what is EMF here? L into dI1 by dt. Is anywhere this equation, this R is coming in this equation? It's not coming. So even if R is present, see what you notice here, see even with the R is present, potential difference available to combination of inductor and resistor remains unchanged. Even if R is connected or not connected, potential difference across L and 2R always remains equal to V, even if R is connected. So presence of R does not alter the current I1 at all. My equation remains same whether R is connected. If R is connected also, so V is the potential difference available across two R and L at all times. If V remains same, correct, this also remains same. So in this case also, that's what they are asking. So what is the time constant in case of charging? So if I look at time constant for charging here, time constant for charging will be equal to, remains same. It will be L by 2R. And what happens to discharging? What is the time constant? L by 3R. So this question is based on tau for charging is equal to L by 2R. And for discharging, L by 3R. Shravani, have you understood this?
Yes, sir.
Have you seen something similar elsewhere in any other topic?
RC correct.
RC. This is something similar. So what we have seen in RC circuit, similar thing happens here. Even RC also something like this, exactly something like this happens. Had this resistance R been connected here, the answer would have been different. Okay, so some of you can think of, if I have another R connected here, what would be my, then the case becomes very little complicated. We are not doing that right now. Okay, so if disconnected like this, it remains same. The reason is this: the equation remains unchanged by presence of R. Okay, so you can think of, you can go to basic equation. This basic equation determines the value of time constant. Okay, this gives you value of L by R. Here also it comes L by 2R. Okay, there are some simple questions based on time constant. Let's say about some of the questions are very simple. This is also part of assignment. This is very easy to question to solve. What is the time it takes for current to go to 63%? How much time it will take?
Tau by 2.
How much? It will take, T will be equal to tau. So this in the current in the solenoid grows to 63% of its finally steady state value in 0.3 seconds. It basically is saying the tau value is equal to 0.3. So what does this 0.3 indicate? This is nothing but tau. Time taken to reach 0.63 times the final current. It's something like this. If you look at the graph also, the steady state, how the current varies. So what we have in case of RC circuit, we have graph for Q and T. Here we had current graph for I and T. And it's something like this. And this is something what we call a steady state, but afterwards current doesn't change. This is I naught, which is V by R. So, and the final state, the current is equal to 0.6. What is 0.6 equal to? 0.6 is equal to V by R. So these two values are given. Can we find value of L? This is also a simple question. This is also part of assignment. All of you can solve. It is easy question to solve. We'll go through, these are nothing but application of formula. So these are all based on application of formula. This is also pretty simple. A current in LR circuit builds up to 3/4 of steady state value in 4 seconds. This also straight application of formula. So this also based on I is equal to I naught 1 minus e raised to power minus t by tau. What is given here? I is equal to 3/4 of the steady state. I is equal to 3/4 of I naught. And at what time? At t is equal to 4 seconds. What is the time constant? For this equation, all rest of the terms will cancel out. We can easily find value of time constant. These are simple application of formula. This also part of this, all of you can easily solve. And in LR circuit, current t is equal to 0 is 20 amperes. After 2 seconds, it reduces to 18 amps. What is the time constant of the circuit? Compared to previous question, this question has slight bit of difference. What is the difference it has compared to the previous question? Shreya, can you spot what is the difference here? Previous question I used the equation I is equal to I naught 1 minus e raised to power minus t by tau. Shreya, can you tell me what is the difference in this question compared to previous question? This is the equation what we have for charging. Kaushik?
Yes, sir.
Do we notice any difference compared to, do we use the same formula here in this question or slightly different formula?
No, sir, this is discharging.
Very good. And also the moment current turns out, this at t is equal to 0 is 20, that becomes my I naught. This is a discharging circuit. If it is discharging, so moment I notice current is decreasing, it is a discharging state. And moment is discharging, pretty simple, I'll use the discharging formula. I is equal to, I as a function of time is equal to initial current, e raised to power minus t by tau. And simple substitution, I get my answer. Very simple. And after 2 seconds, it reduces to 18. So this also is simple. Only thing we notice when it is charging, when it is discharging. This is a slightly tricky question, a nice question. So all of you look at the question, can someone spot the logic? Can someone find an answer, which option is correct, and give me a reason why whichever particular option is correct? So give you a couple of minutes to look at the circuit and try to spot, and the answer is pretty simple. So all of you have a couple of minutes. So what is happening here? So this also is a typical LR circuit. There's an inductor, there's a battery, and E is there, R is there, L is there. What I'm saying, this is something we make some changes. One of the things is changed. So there are two circuits, but actually only one of the three has been changed. So first case, this is circuit. Second case, this is circuit. So question what they're asking, which of the parameter has been changed and has it been increased or decreased? Okay, that's what the question is. Bhagishri, can you answer this question? You have done similar question in RC circuit. Do we recall having done this question in RC circuit?
Yes.
Okay, so can you try and answer this question? What basis, what is the logic, how do we answer?
Both are starting from the same point.
So that is, any charging will always start from the same. The first point is starting from same point. So one is starting from same point, but basically actually in this particular case doesn't add any new information from starting from same point. Okay, which is charging. So basically both are given from zero charging state. What else we notice here? You notice this is what the question is. They're asking which parameter out of these three, which has been changed and how. So what is second thing you notice here, important point here? We had done something similar. This is not coming to mind immediately. Okay, Disha?
Yes, sir.
Can you recall something similar done in case of RC circuit? Can we apply a similar logic here as well?
Yes, sir. Like the total current flowing is same.
So let's look at, let me write. Basically what you're saying, the final current is same here. That's what the single line is done. So if final current is same, I equate those terms. What is the final current is equal to? In this case, if this also final current is, so what is final current equal to? I would have written E by R is equal to E1 by R1. What does this imply? So either if these two ratios are equal, either both are changed or none are changed. One cannot be changed. If the ratio is same, so it implies either both E and R are changed by same proportion, or then only ratio remains same, or none is changed. This also is easy to understand. And in this case, since only one has been changed, this is not possible. So if final current remaining same implies both E and R have not been changed, none have been changed. So this implies final current being same implies that L has been changed. So L has been changed. So L and L dash are not equal. So then how do you spot whether L is increased or decreased, Disha? Next final.
Oh, yes, sir. In first case, the tau is more.
Okay. So basically, how do you spot tau here? I draw a line which is equal to 0.63i.
Yes, sir.
And correspondingly, if I take this term here, this is my tau 1 and this is my tau 2. Which tau is more?
Tau 2 is more.
Tau 2 is more. Is it clear? Easy. So that's why it is reaching final current. But second case, it is taking more time. Let's see why it is taking more time. So what we notice, second point, what we notice in tau 2 is greater than tau 1. And what is tau equal to? L dash by R is greater than L by R. It means R are same both. So this L dash is greater than L. It means inductor. So this is what we also understand in circuit. As inductor value keeps increasing, it takes more time to reach the final current. If inductor is very small, if inductor is 0, it will reach the final current almost instantaneously. You understood this point also? What happens if L is negligible? It will reach the final current almost instantaneously. Immediately it will reach the final current. That's what so far what we had dealt in the previous cases, it reaches final current also instantly. As L keeps increasing, it offers more resistance to rate of change. It takes more time to reach final value. So answer here is L is increased. Okay. So all of you have understood this also. This we had done similar thing in RC circuit. This question requires logical deduction. It's not just application of formula. Okay. Next one. How do you calculate charge that passes through battery in one time constant? How do you calculate charge that passes through the battery in one time constant? Advay? Okay, so this is, we know in this circuit, as soon as you close the switch, the current will grow over a period of time. Initially, current grows at a gradually reducing pace, and finally, it reaches a steady state. And we know it reaches this is things we know. It reaches 0.63 times of steady state current at time t is equal to tau. Okay, so what we need to find? We need to find how much charge will pass through the battery in one time constant. What is the charge it will supply? So how should we calculate? What is the method of calculation of charge that passes through the battery in one time constant? What is the method of calculation? We know value of current. This is something what we know here in this case. If I had to write one equation which I know, I is equal to E by R 1 minus e raised to power minus t by tau. Or I could have written simply I is equal to I naught 1 minus e raised to power minus t by tau, tau being equal to L by R. This is the equation I know. From this equation, I need to find the value of a charge that will pass through. How do we find charge that will pass through? Just can you tell me what is the charge that will pass through?
So we have to integrate with respect to time, right?
Yes. Basically, whenever you have to calculate what is current is equal to, current is equal to, at any instance, the current rate of the charge through. So what is dq? And dq we have seen earlier also, dq is equal to I dt. So this indicates what? This indicates if this is the current, in time dt, so much of current passes through. So what we need to do, if we have to find for longer time interval, we have to sum up all the charge which has passed through. How do you sum it up? Using process of integration. If I integrate from T1 to T2, it will indicate charge that has passed through point T1 to T2. Or if I want time from 0 to tau, I'll integrate from 0 to tau, IDT. And in terms of graph, what would this indicate? This would indicate area under the curve between 0 to tau. Thus area, that's a charge that will pass through time 0 to tau. Is this a difficult integration? This is a fairly simple integration. All of you, this also part of it, all of you should finish it by evening today. This also part of the simple direct integration. Is this clear now? So this also you can all integrate and you can easily find what is the charge that will pass through, and we substitute tau is equal to L by R, we can easily find an expression. Okay, can someone spot in terms of they all have different dimensions? Can we spot eliminate other option based on dimension analysis? Which dimension is not matching with the charge dimension? What does term E indicate? This is exponential term. So this is a constant. So can we spot based on the this term also? You can do so. So whenever some options are given and nothing else, you can, all of you should try. Can I spot which one? You should get a dimension equal to of charge dimension. Okay. Or current into time dimension.
Third option.
Current into time dimension. So you can easily spot, yes, third option. So even without solving also, we could have got an answer. Right now, our objective is not to eliminate option. You can integrate and solve, but I could have done so because all these options given here seem to have different dimension. They are arranged in different way. So we could have done that also. Okay. So let's next one. Next we come to something about, we just talked about the capacitor stores energy in form of charge. We have briefly mentioned, we have seen in case of discharging. In case of discharging, where from the energy for current flow comes. Energy for current flow comes from the energy which has been stored by inductor. Let's see how is the energy stored and how can we quantify the energy stored in an inductor. Okay, and I think prima facie, even before we get started, I think some hint is already there. In case of capacitor, energy is stored in form of a charge. Greater the charge is for a given capacitor, greater is the energy. So as the charge keeps increasing, it's storing more and more energy. And when the charge starts decreasing, which is called discharging state, it is supplying energy. Here also in case of inductor, which form, as our current keeps increasing, it keeps storing energy. And when the current starts declining, it means it's releasing energy, supplying energy. Let's see mathematically also how it makes sense. And mathematically also is very simple expression. Basically what we do here, the circuit, and why we have drawn something like this. You know, as long as current is changing in the circuit, see, inductor behaves like a battery if the current is changing. So what you can do, we can replace, an inductor has some resistance. The resistance the inductor has already been shown here separately. And this R indicates the equivalent resistance of the whole loop. This R could include resistance of the battery, it could be internal resistance of the inductor, external resistance put together. Why we have shown as EL here? What does this indicate? This term indicate here. This term indicates induced EMF. So whenever the current changes, the inductor behaves like a battery. So here we have taken case when it is started, we have connected, the key has closed. So current is increasing. As the current is increasing, which direction the EMF will, it will develop an EMF which will tend to oppose the increase by trying to drive a current in the opposite direction. So this is EMF EL, and EL is equal to L di by dt, this is orientation. And we have seen earlier, we have used the same equation in case of derivation of current as a function of time. This is application of Kirchhoff law. Okay, what we do from this equation is valid at a particular instance. What we have done in this equation, we multiply both sides by term IDT. IDT. So this becomes I into E dt, and this is the term here. Okay, so what will the unit, what will the unit of each term, what would each term indicate? Can anyone tell me what would each term indicate here? what does each term indicate? What does I square R indicate? Power. What does power into time indicate? Energy. So each term is indication of energy. Each term is indication of energy. So let's understand what energy does it indicate. So when we notice here, when we do something like this, each term is energy term. And what does IE dt indicate? Can someone tell me what would this term indicate? This energy. Can someone better define this term here? What does IE dt indicate?
Energy supplied by battery.
Energy supplied by battery in time interval dt. This is the term. Perfect. So this is the term, energy supplied by the battery in time interval dt. And what would this term indicate? And this is nothing new, but basically no power into dt. But this energy dissipated in the resistor in time dt. And if this equation makes perfect sense, this energy supplied and this how it is being utilized. So some part of energy, this is energy supplied to the battery. Partly it is dissipated in form of heat in the resistor. What about the rest part? This is the energy which is stored in time dt in the inductor. Okay, does the whole thing make logical sense here? Gayatri, can you repeat what I said? Gayatri?
Yes, sir.
Uh,
Sir, in that equation,
what are these terms here? We see. Huh?
IE dt is the energy supplied by the battery.
Battery in time interval dt. I dt is energy supplied by the battery. And what are these other two terms here?
I square R is
What
power,
is this?
and power in dt time is energy.
Energy, perfect. And what is this power? This is something, how would you use this term? How can we state in words? This is heat dissipated in the resistor in time dt. And what is the final term? So how do we interpret all three terms here put together? How do we interpret the equation? In terms of energy, again, let me repeat, we can interpret this equation. This indicate energy supplied by the battery in time dt. And the energy what is supplied, it will be going to use some different forms. So this energy, part of it is dissipated as a heat in resistor. Remaining part is stored in inductor. Why do you think it is stored? Because we notice after the battery is disconnected, there is still some current flowing in the circuit. So that gives indication, okay, the inductor stores that energy and it supplies energy when battery is not there. And later on, when you conduct the experiment, also it matches. So that's what, Vignesh, you raise your hand. Any query?
That was my doubt, sir. How do we know it's stored or dissipated?
Correct. No, so that's something. What is the indication for that? Because when we see something like this is there. So suppose initially when I have connected S to A. S2A is what is happening at the time. S2A, that case current is flowing, it is supplying energy. And suddenly if I switch the flip the switch from A to B. Now this becomes my circuit. Is there any battery in the circuit?
No, sir.
No. And if I observe this is bulb here, after as soon as I flip the switch, still after that also if I see light here, where from this energy is coming? What do I understand? Where from the energy in the resistor is coming? If this bulb is still lit after this switch has been flipped from A to B, energy can't be coming from the battery then. Your battery is not part of the circuit. Where from the light is coming? Where from the glow is coming? It must be some form of energy which has been stored. Only thing which is different from the rest of the circuit is inductor. And what we notice here, can we conduct in the experiment and find out, okay, once I connect inductor and I connect different inductor and different current values, and I can measure what is the heat dissipated. And I find, okay, every time it matches up and we find, yes, so this is something partly it is intuitive, partly logical and partly experimental. All of them put together, it gives indication it matches up. So fact that current is there in the circuit which is not having battery after battery is disconnected indicates there's some source of energy. And what is source of energy? Only source of energy is inductor. Okay. So energy supplied battery is equal to energy dissipated in the resistor plus energy stored in the inductor. So this is the energy stored. So what we notice from here, okay, so this is something, this energy is stored. So here, so in this circuit, what is happening? I is changing from 0 to final current value. So if you have to calculate, this is du, energy stored, di by dt. So what is the total energy stored as the current changes from during charging state? Charging state is changes from I to some, at some instance the current is at time t is equal to I. So when the current I is flowing in the inductor, it will have energy equal to 1 by 2 I square L. Thus energy is stored in the inductor. Okay. So what it indicates, as the current keeps increasing, energy stored also keeps on increasing. When is the energy stored in the inductor maximum? When the current is maximum. Thus when energy stored is maximum, and you can calculate. And this energy, as the current, when what happens in the discharging state? Discharging state, the current drops from the initial current to 0. So in that case, energy stored in the inductor is getting released. Where would that energy go when you are discharging? Where would that energy go? Can you measure the energy? Where has the energy gone? See, as we are saying, as current increases from 0 to I, energy stored in the inductor also increases. This energy is stored. And how do we make sure? How do we convince ourselves this energy is stored? When I switch the flip from A to B, when this is a circuit, I find this resistance also, I see either the light, or if it is a heating coil here, I can some heat being dissipated here, even after the switch is closed. So if the heat is dissipated, typically if inductor is not there, as soon as you close the battery, the current drops to 0. So if in presence of inductor, if the heat is being produced after battery has been removed from the circuit, that heat can only be coming from some form of energy stored in inductor. How much that heat would be, so that's what we can calculate. So in this case, so this is the energy 1 by 2. We also calculated energy density in case of capacitor. Do we recall how did we calculate energy density in case of capacitor? What does energy density mean in case of capacitor? Nitya, do you recall how did we calculate energy density in case of a capacitor? And what does this energy density mean?
Energy per unit volume.
Energy per unit volume, simple definition. And where is the energy stored in case of capacitor? We assume the energy is stored only between the plates of capacitor. Why did we assume that energy is only between plates of capacitor? Was there any logical reason? Why did not take the rest of the volume? Why only plates of the capacitor?
Field exists in that volume.
Field exists only in that space. Okay, so something similar here also. So what we do, something similar, and this gives a very great insight. So what we understood in case of capacitor, wherever there's electric field, if a space has electric field, wherever the electric field exists, there's energy in the space. So presence of electric field indicates energy in the space. And when the sun rays or light, when the rays come from sun to earth, there also, as the sun rays travel, it creates electric field and magnetic field. And presence of electric field and magnetic field indicates presence of energy. And as the energy changes, the energy flows. So, and that is something that was a theoretical understanding, and a concrete proof was in form of the way energy is transferred through EM waves. So their energy density. So similar way also we have taken in case of capacitor. In case of capacitor, parallel plate capacitor, advantage was energy was confined, because only in the space where field was there. The similar thing we do in case of solenoid. Solenoid also we make a simplifying assumption. What is the assumption we make here? Here also we assume that energy is almost entire field is confined within the volume of solenoid. Okay, it is not as, but even in case of capacitor, is the field only between the plates of the capacitor? Actually, ends of the capacitor, there's a fringing effect. Some of you recall this fringing effect here. So there's some field outside, but we neglect this field. So there's some decrease, some fields which are similar way in case of solenoid also. There's field outside the volume of the solenoid. But what is the assumption we make? And we later on we find this assumption matches in so many circumstances. That's why this assumption is taken to be valid one. We assume the energy is confined only within the where the field exists, and major portion of the field is only within the volume. The field is, and we have the field is constant, similar to what we had in case of capacitor. Hence we can write in this term. So what we do, so energy density in solenoid. So how do we calculate energy density in solenoid? A very similar way. I'll write the total energy and the divide by volume. So 1 by 2, I square is okay. What is the induction, self-induction of a solenoid? It is equal to mu naught n square into volume. This is our previous derivation, very simple derivation. L is equal to flux in the solenoid when the unit current is flowing, or L is equal to flux per unit current. That is mu naught n square V. If we divide by V, thus the VV term cancel. Thus the energy density in the solenoid. What we do there also, we wanted in case of capacitor, we have converted into electric field. Here also we'll convert into magnetic field. How is the magnetic field related to these terms? We know magnetic field B is equal to, which can be treated as uniform all through the volume of solenoid if it is an ideal and long solenoid. So mu naught Ni. In place of, so what we do, in place of Ni as substitute B by mu naught kind of thing. What we do, this is energy density. So in place of I, what is substituted? B by mu naught n. We substitute this value, mu naught n square remains same. We get energy density is equal to B square by 2 mu naught. And if you recall, what are the similar expression in case of energy density in case of electric field? It was E square by 2, sorry, epsilon naught E square by 2. So there in Coulomb's law formula, epsilon naught was in the denominator, energy density comes in numerator. Here in case of Ampere law, and mu naught was in the numerator, but energy density comes in the denominator. So there's a kind of similarity between the two. What does this indicate? Wherever there's a magnetic field contains energy. So energy is stored in the inductor in form of magnetic field. Energy is stored in an inductor in which form? In form of magnetic field. So any space, if we know what the magnetic field is, we can calculate the energy stored in that space. That's the energy density, and we'll continue from here in the next session. Okay.